Okay, so let's go through this example, okay? In this example, we can think a bit of the event that we care about as being the probability of rain, okay? So we care about whether it's going to rain tomorrow, right? So let's say that we have some information, and the information is a forecast. Okay, so I don't know what's your favorite forecaster, but let's say before we hear the forecast, we have a guess. So the probability of rain is 80%. It rains quite a bit here, and in August, and 20% that it's not going to rain. Okay. Now, let's say also that there is a probability that the forecaster is correct. Okay. So what does that mean? That when it does rain, right, the probability that the forecaster will have said rain is going to be 90%. Okay. So rain is correct related 90% of the time. Okay. Let's say also that when it doesn't rain, the forecaster is correct 50% of the time. Okay. What we would like to get now is that given that we have a forecast, let's say x1, it's going to rain, then what is our belief that it's going to rain now? So that will be the probability of omega 1 given x1, right? So you can go through this calculation. You can go through this calculation if you can, and I will try and help you along. Okay? So the first step is to replace this A and B here with these events there. And see that if you can get into a form where this thing can be written in the form of this fraction. Okay? That's the basic idea here. And you should be able to remember these rules, okay? And there's one other rule that I forgot to write here. The probability of a certain event happening is 1, and the probability of nothing happening is 0, okay? That basically means that if you have some event A, then the probability of A happening or not A happening is 1. The probability of A happening and not A happening, which is completely impossible, is 0, okay? So in this particular case, A1 and A2 have the property that they are not only disjoint, so they overlap, but also they cover the complete universe. So the probability of A1 and UA2 is 1. Okay. So here you should hold that this holds for omega 1 and omega 2, right? So it either rains or it doesn't rain. Yeah. And the forecast is either rain or not rain. So they're not any alternative things that can happen. Okay? So here I told you this is a typo there, so I'll have to fix it actually. Has anybody noticed the typo yet? Well, it's not really a typo, but anyway. Let's write it like this. So okay, so that's fine. I'm just missing one more thing. That's fine. So you see basically this term appears always on the denominator, either here or there, depending on this event you're talking about. And yeah, that's fine. So what you need to do to solve the exercise is pretty simple. So we can identify omega 1 or omega 2 with this A, right? A1 and A2. And we can identify the probability of, let's say B is one possible event for the, let's say X1 or X2. So we can identify X1 with B, right? And then you can try and plug in this value there. So it shouldn't be very difficult. Okay, let me go through it a little bit. So how should this work? We want to write, first of all, P of P given AI, right? Or in our case, it's going to be probability of X1 given omega 1. Okay, let's say that the forecast was X1, right? Times P of omega 1, right? So we have set this to be 80%, so 0.8. And we said that the probability of the forecast being correct when it's raining is 0.9. Okay, so that's one term, and the other term is probability of X2 given omega 2, and probability what we have, 0.5. Okay, but what we actually want is probability of X1 given omega 2, right? How much is that? Why? So what do we know? We know that omega 1 and omega 2 are exclusive, okay? So, and we know that they have probability 1 together, okay? And also the forecast rather says rain or no rain and nothing else. So we also know that P of omega 1 or X1 or X2 is equal to 1. So he either says that one or the other, so it's also 1. Okay, so this has to be, this holds also for any conditional that we do. So probability of X1 or X2 given anything else, like omega 2, also has to be 1. Okay, unless it's completely 0, in which case we don't care about it, but the sum has to be 1. They are mutually exclusive events, so it has to be 1. So now we can use the same idea. So because they're mutually exclusive events, that means we can separate them. So that means that px1 or x2 given omega 2 is probability of x1 given omega 2 plus p of x2 given omega 2. Okay, that's because of their mutually exclusive events. So now we know that this is 1, right? And we know that this is 0.5. So that must be also 0.5. Okay. Fine. So now I have solved this one as well. So now we can write the whole thing. P of x1 given omega 1 times p of omega 1 times p of x1 given omega 1 times p of omega 1 plus p of x1 given omega 2 times p of omega 2. Okay. And this one we have 0.9 times 0.8. And this one we have again the same. Here we have calculated 0.5 times 0.2, which is the prior probability we had of having rain. Okay, so if you do the calculation, you get something like between 90 and 80%. Let's see exactly what we get. So this is what you get. And if you do the other calculation, what's the probability of having rain, given that you have the forecaster said no rain, you see that your probability of rain is slightly higher than it was before. Okay. So you believe 80%, so it goes down to 44% because you don't really trust the forecaster that is correct. Okay. So that's the general idea of Bayesian inference, and you can use it for this kind of probabilistic framework where everything is probabilities, but it's also a bit more general than that. We have also seen classification in terms of conditional probabilities. We can also write it like that. So let's say you have some observations xt, which is what the class, the observations describe your data, and you have some class level you want to predict. And let's say you somehow get from somewhere a probability model. That means what's the probability of some particular observations xt given yt. And let me just switch a bit here. So you can see this as a kind of rough model. You have 3 classes here, and for every class you have a histogram of the alcohol content. So it's like a distribution of this particular feature for every class. Okay, it's not an actually correct model, but it's some approximation of the model. But you can think of it as a model for illustration. Okay, so for these 3 types of wines, you have different distribution for the alcohol content, and you can think of this as representing this model of what's the distribution of the features given the class label. Okay, so now you can think about classification in these terms. You have some generative model that tells you what's the future distribution for a given class label, and you also have a prior class probability. Maybe some classes are much more rare than the other classes. If you have all these things exactly correct, calculated, and so on, somehow from magic, doesn't matter where they come from, if you have them, then it's very easy to calculate the probability of a given class given your new data. Okay. The basic problem, however, is that it's not trivial to calculate this. Maybe this is simple because there is only a few classes and you can do it, like in this wine example. But imagine a problem where you are Google and you're doing image annotation. Okay, you have all these things you can annotate in images and all these combinations of things, green dog on blue field or I don't know what. And well, there are too many classes even, so even this thing is kind of difficult to calculate. Okay, but you can get some estimate of it and you can create these kind of models. And in analogously to the diagrams we showed before, this basically tells you have some model, and given the model, you have a probability for class labels, And given the model and the class labels, you have probability for observing specific data. So this kind of illustrates how the model is supposed to work. So the model is supposed to give you probabilities for labels of classes, and it's supposed to give you probabilities of observations for specific labels. So these arrows kind of describe the structure of your model. And it doesn't have to apply, this kind of graphical structure doesn't only apply to this kind of probabilistic models, but you can use it as a general tool for describing any model you want. Okay? This is why we're going to focus on that a bit. So there's a simple example here for seeing how this works. It's basically the normal distribution. Here you say that for any given feature you have a normal distribution of observations, and you would like to calculate the probability of the class, this one here. Okay. So if they have equal variance, then your class probability is basically going like this, because both of them have the same variance, so they both have the same kind of shape. And there is a threshold here where you switch from predicting class 1 to predicting class 2. Now, if they have unequal variance, so this one has a wide variance, so it's much wider. So if you go to the tails of the distribution, the tails are higher than the tails of this one. That means that you're only sure it's class 2 when you're around this peak here, and when you're around here, then your posterior says it's class 1. Okay? So this is more like a background noise class, and this is more like a one specific class that is very kind of sharp. And there's also the effect of the prior distribution. So if you have equal prior and variance, then you have a threshold like this. But if your prior is shifted towards one class, then your threshold shifts towards one class. Yeah. Even though the distributions of the features are the same. Okay. So now in this class we will talk a lot about subjective probability. So I said these probabilities come from some model and so on. And these models describe probabilities, but we don't know the model itself. Okay? So we're usually going to assume that there is some model that is true and we have some belief about what is the right model. So say I believe I'm a better basketball player than you, it's just a belief. That is not true maybe. But we would like to assign probabilities to any arbitrary event. And because they are not really tethered to the reality, but they are kind of specific to what you think, I would give a special symbol and Xi. And this is exactly the same as probability. There is no difference. I'm just going to say we're using Xi for everything subjective, and for everything else we use P, just to make it clear. But it's all probability. So imagine that you are the rat in the maze. You have two possible models for what your maze is like, either this one or that one. Okay? And you have some uncertainty about what's the right maze. Then you go around the maze and you observe some history. So you move around and you see where you're going. So based on this evidence, you have some conclusion. Okay? But maybe this is not possible to do here, because I went to the center, there's no corridor in this model. So this model of the world is correct. Yeah, so every model of the world basically assigns a probability to the history that you have observed. So now, the standard Bayesian update is what I described before. It just says multiply your prior with the probability of observing this data, and then just normalize by dividing everything with everything else. And you have your posterior distribution. And in this particular case, the probability of observing this thing here is 0 under this model, because there's no way you can go through here. So then the probability of this one becomes 0 and this one becomes 1. Okay? So these models are in some sense plausible models that could be real, but your belief is something you arbitrarily select. And this is why we just give a different name to it. Okay. So there's an example we can go through a little bit today, but we will go through it in a bit more time. So let's say that there is a person that says they're a medium that can predict coin tosses, okay? Say I throw a coin a few times, and then I predict it correctly 5 times. Okay. I throw it 5 times and I predict correctly. Are they really able to guess or not? Yeah? What do you think? So first we have to specify 2 models. What should happen if the person is a medium and they can predict, and what should happen if they are not a medium and they cannot predict? Okay? If we do define these models, like the rat has 2 models for the maze, we have to define 2 models for what the medium can do. Then we are able to make a conclusion and say, well, because this model of the medium said that and this is what happened, then I now believe it's a medium or not. Okay? There's also the question of how likely we think that John would be a medium in the first place, right? So if we think it's very unlikely, then we put a low prior probability to this. Yeah. Yeah. So the summary of this: have some mutually exclusive models, right? Have probability for data. You can see it in two ways for every model, and have a probability that the model is correct, and then we have the posterior probability, like we explained before. It's nothing is different here. Just give slightly different notation to separate the model distribution from our belief about the models. So this is what the model says, and this is what we think about the model. And this is basically the summary of that. So now I would like you to start thinking about this exercise, which we will go through next time, okay? Because there is not enough time to go through it. But let's say we want to select some model for the medium, okay? So let's say you want to predict coin tosses. Okay. So let's start this exercise now, actually. So what I'll do is I'll do a sheet. Okay, and I'm going to share this sheet as like predictions. Okay, and then I will write here one. It's kind of slow. One, 2, 3, 4, 5, 6, 7, 8. So write in, for example, 0, 1, 0, or 1, depending on your prediction. So these are your predictions, okay, for what the coin is going to be like, okay? Just write in whatever you like. I will not see them. I will just generate 8 random numbers, and we'll see how often you actually get it, okay? And this is the link. Copy link, and is there a way to make it shorter? I don't know. Where should I put it? Huh. No, I'll put it. Yeah, so just add it there. Just homework, okay. So this is your homework that you can start working on, and you don't have to finish it, just think about it. Fill in predictions, okay. Everyone take one line. I think you can remember which one is your line. And then think about the models. Think about them now. So what is, yes?
It says I have to request edit access.
How would you? So what is the right model for the medium, and what would be the right model for a non-medium? What do you think? Can edit. Right. Yeah. So what do you think is the right model for a medium, and what should be a right model for a non-medium? So if you're not really psychic, right? Could you still be able to predict the coin tosses? Yes? Why?
Always a chance.
There's always a chance. I mean, better than, should be able to do better than chance, like 50%.
If it's possible to predict with a higher probability than 50% one coin toss?
Yeah. If you have many trials, so you say have 100 trials. It depends on the coin, right? So if the coin is not if it's a biased coin, so it comes most often head than tails. If you try it a lot of times, then you will be able to tell probably, yeah, if it's biased or not. And then you might be able to predict better. Okay? Or if the way that somebody throws the coin is obvious, that which way a coin will come, you might still be able to predict. Or if somebody's cheating, you can still predict. Okay? But even take the simplest example, coin tosses are not completely random, you might be able to predict them just because somehow the coin lands more often head than tails. Okay? Then what should the model be, right? So we'll go through that a little bit next time. But for now, we just assume that the model of the medium is always predicting perfectly well, okay? And the model for the non-medium is just completely random. So and not able to do better than chance. And of course, we have also independence property, which is fine in this case, but if we have this learning model where somebody can learn that the coin is more often coming heads than tails, then this doesn't hold anymore because they will get better with time. Yeah. So the probability of predicting correctly will increase with time. Yeah. So it's not trivial to define, let's say, this in general, but we can do it for specific models. Anyway. Okay. So what you should be doing is for every possible data that you see, you can calculate the posterior belief, and you can also predict the probability that the person will make a correct prediction. Okay, so if you have all finished, yeah, I will write here the true thing, or I will write down here. So this is the true thing. It's completely random. I use my magic random number generator. Okay, well, too many ones. There's one more here. Okay. So I don't know if anybody managed to guess this exactly, but this is what I randomly generated. Okay. So from this one, right? Someone predict full zeros. Fine. So basically here you can see is anybody else, anybody agreeing with everything, right? So that's basically the whole thing. So if you have zeros, these people have 2 zeros. This person seems to have just copied what I wrote. It's fine. So this person just managed to predict everything. Is there anybody else? Actually, this one too, right? Number 6. Or no, almost. But yeah, so this one seems to be not a medium, right? Nobody seems to be a medium apart from this one, right? So the thing is that if we had, let's say, 1,000 people, probably at least one of them would have done it anyway, right? Yeah. So just by chance. So should we just say that the probability of this person being a medium is 1 or what? It depends on the prior, right? Yeah. What should the prior be that we select? Okay. And what about if the person that is a medium is not really perfect? It's like quite good, but not perfect. Yeah. So how should we do it? Okay. So as an exercise for next time, we will start working on this idea. It's exactly the same thing as before with the stations. And what happens is that every station gives you the probability of rain given the past. Okay? Use it for the whole week, right? So the CNN, the Swedish one, and the Norwegian one, give probability for rain, and this is what actually happened. Okay. And we would like to write some very simple Python code. The one I wrote is like 70 lines, where we update our belief at every step. So we start with a simple vector. The vector of probabilities for every one of these stations. What's the probability of they being the right model? And in this setting, you can think of it like every station has a chance of being really the right model. So the actual rain probability is exactly the same as that described by one of the stations. Okay, it's not true, of course. Okay, none of these stations give you how to have the correct model. But a lot of times we have to work with this assumption that have a lot of models we want to choose from, and one of them is as close to real as we can get. And then here we can say, okay, we have these 3 meteorological stations, and one of them is as close to real as we can get. If one of them is the best, then what's the probability of a particular one being the best? So initially we can start by saying that they're all equally likely to be the best. And then using this idea of posterior updating, we would like to be able to calculate on the fly the probability of each one being the best. Of course, at the end, it's pretty simple, because you just multiply the probability of all these things, and you get the answer. But building online is a bit more interesting, because you can have intermediate idea of what is the base station without having to wait for all the data to come in. So you can update your belief about what is the base station every day. Yeah? So as an example, the first day every station has 1/3, okay? But then when you observe it's raining the first day, then you basically multiply by 0.6 the value of the first station, the value of the second station by 0.3, and the value of the third station by 0.5. And then these values you normalize so that they sum to 1. Yeah. Okay, let's see. Okay. So you have the stations, and every station gives you the probability for rain, okay? And you also have the probability of the station, and you know if it's raining or not raining, right? So now your probability at time 1 of the first station being correct is just the probability of the station being correct given that it rained, yeah, and that just basically the probability that it rained according to the first station times the probability that the station was correct, sum over all the other stations, okay, and then this gives you your first time step estimate. And in general, you can basically have the next step probability is always basically like this, okay, more or less. So you just update your belief at every step by just using your previous step belief and doing this calculation here. So in terms of programming, it's pretty simple actually. In terms of getting a better understanding of what this means, it's slightly more complicated, but I encourage you to play a bit with it around until we meet next time, and when we'll actually program the whole thing together, okay? Slowly, okay? Right. So the basic idea is that when the data agrees with the station predictions, then you increase the probability, and this is what this calculation tells you. And you reduce the probability of the stations which don't agree with the data. You can do it at every step. Okay? And this don't even have to be probabilities. These things here could be any arbitrary score that is positive, and you still get the same result. And there are lots of theoretical results that prove that if you do this kind of thing, then you end up finding always the best station, or more generally the best model, as long as you have a finite number of models. So this is a very, very simple calculation, and in many different contexts is the right thing to do. Okay? In some other contexts you have to modify it a little bit. But it does give you a good way to represent the uncertainty you have about what is the right model. And it does take into account both the number of models you have and how well they fit the data. Okay. Let's take questions, if you would like. So the methods you would, by the way, the methods that you would use is basically you should have some method for get posterior. That would be a useful method. So you have a prior model, right? It's a vector, and you have an observation, and you have model descriptions. So you should have a method like this that gives you the posterior given a description of the models, or rather what is the probability. You can just replace it with predictions. the predictions are basically these probabilities, and the observations are what you actually observed, and the prior is this thing here, and the return should be this thing here. And one helper function should be get marginal, which just depends on the prior and the predictions. So these two methods are all you need, and this second method just calculates the sum here. And you should be able to do this exercise. Okay, I think that's okay for now. So just to make it nice and slow, especially now in the beginning. I'm going too slowly, I don't know. You can tell me. I know there is a bit of varied background here. So, what do you think? Too slow, too fast? Okay. I mean, how many of you are already familiar with Bayesian inference? How many of you are already familiar with Bayesian inference?